Hey guys, it's Thursday, last day of the week for us. Remember, all homework assignments will be due tomorrow at noon. It'll be Friday. If, again, you have any troubles meeting that deadline, just let me know, and you can either submit them via Blackboard or via my email, which is available on the website. Today, we're going to be looking at our last kind of basic topic. Many of you guys, I imagine, are looking at the first few weekdays and going, too easy. Perfect. Good. That should be the goal. But there are some that still make mistakes all the time with this kind of stuff, and usually it's because there's a misunderstanding somewhere. My goal the first week is to get those kind of misunderstandings some time and ability to get some checks on them. Make sure that these first few assignments, you should be shooting for 100% every time. There should be zero mistakes. That's how you know you're ready for college algebra. It's not that this stuff is easy, but if it's easy and you get a 16 out of 20, then it wasn't easy. You're making mistakes. And those mistakes need to be fixed. Because as mathematics grows in complexity, the steps we're talking about don't disappear. They become steps along our bigger path. And so this might be the fifth or sixth thing that you do in a problem. And you don't want to be making mistakes there. When it's so easy to make mistakes, when it's difficult. Okay? Think of it this way. If you, since you guys should be able to drive, let me make a driving example. If you're driving down the road and you can't figure out which pedal is the gas or the brake, it doesn't matter how good a driver you are. If when the situation calls for it, you hit the wrong one. Okay? You have to be able to make the right move at the right time. And that goes doubly in a math setting, because if you make a mistake, there's not always somebody there to watch your back, unless you're working with a team on a project. And at the high school level, that isn't common. You're expected to do a lot of things solo, which is a shame. You should work to make sure that at this point, you are seeking perfection. Zero mistakes. And if you find a mistake, don't hold that against yourself. Instead, use it as an opportunity to go, okay, maybe I rushed this part. Maybe I make this piece too complicated. Or maybe I didn't pay attention to this thing. Or I just did something silly that I would never do again. But note when it happens, and seek perfection when it's easy. Okay? For today, our last major simple topic is going to be about solving for a variable. Now, this is the first time we've talked about when we have an equal sign involved. And because of that, this is where we start to see a lot of the classic mistakes of algebra. So, let's get started. So, let's look at a simple equation. Something like 8 parentheses x plus 3 equals 64. Now, the first thing I want to mention whenever we talk about these kinds of situations is that anytime you're dealing with a problem like this, each side is simplified via order operations. So if it's on the left-hand side, you can simplify it by using any of the order operations and any of the properties. So you can use things like the commutative property, the associative property. For the left-hand side, we can take those steps. For the right-hand side, we can take those steps. And so like in this problem, I can see that I have a distributive problem. And so I'm going to use the distributive property, take that 8, and multiply it to both terms. Because of that, I end up with 8x plus 24 equals 64. Now, at this point, I have nothing left that can be simplified via order of operations, and I have no properties left that can be done to make this left-hand side any more concise. And the right-hand side is a constant, it's 64, so there's nothing we can do there either. And so now we come to the times of an equal sign. When it comes to an equal sign, if you wish to cross the equal sign, there's a couple things to note. First of all, in order to cross, you must undo the operation. In other words, the only way to get rid of something like addition is to use subtraction to undo it. The only way to get rid of multiplication is to use division. The only way to get rid of a power is to use a root. You must be able to undo, anytime you wish to cross this equal sign, you have to undo the operation in order to make that effective. And, last of these, when you cross the equal sign, you usually follow reverse order of operations. Meaning, when you look at an equal sign, the first thing you should look to fix is typically the last thing in PEMDAS. So whenever I'm solving the left-hand side or the right-hand side, I go parentheses, exponents, multiplication, division, addition, subtraction, and I do it in that order. But when I want to cross, I typically go backwards, meaning I'll look to get rid of anything being added or subtracted first. I'll look to get rid of anything being multiplied or divided next. And then once I've gotten rid of those two things, I look for any exponents I can get rid of, or I look for any parentheses I can simplify. And so anytime you talk about these kinds of functions, the best way to go about it is by using reverse order of operations. So as we see in this example, there are two things occurring here. We have a product between the 8 and the x. That is something that needs to be fixed. We also have a sum between the 8x and 24. Now of those two, one of them has to come first. And the one that's going to come first is the sum. Because the sum is an addition problem, which is the bottom of order of operations, and we're doing it in reverse. So if I want to simplify this expression, I need to get rid of the sum first. So I'm going to do that by using a classic step from algebra. I'm going to undo the sum using subtraction. In this case, from both sides, I subtract 24 in order to make this work. So I end up with 8x equals 40. At this point in time, on the left-hand side, you notice that all I have left now is the product. The product between 8 and x, which means that that is the step that I'm going to take. I need to get rid of that product by undoing it, by taking the opposite process. So if it's a product, the best way to undo a product is through division. So I take both sides and I divide them by the same value, 8 on the left and 8 on the right. Now, that ends up with x equals 5, because 40 divided by 8 is 5. Now, here's the thing that most people don't get. Why are we doing it on the both sides? Why do we have to subtract 24 from the left and 24 from the right? Why do we subtract or divide 8 on the left and 8 on the right? Why are we taking these steps? How do we know they work? Well, it works because of one very simple thing. X equals 5 and the equality symbol. What the equality symbol means, in its most basic terms, is it means that whatever's on the left and whatever's on the right have the same value. So no matter what the left-hand side is, it could be an equation, it could be a number, the right-hand side has to match. So at a basic level, you could say something like 1 is equal to 2 over 2. That's an equal sign with a true statement. They're different things, but they have the same value. So 1 is equivalent to 2 over 2. Or equivalent, you might say something like, something simple. X equals something like x over 1. Or 1x. Like, all three of these are the same thing. And so at any point in time, you can replace them and get this equality to stay constant. Take a look back at this problem and watch what happens if we allow x to be 5. All three of the statements we have, this statement, and this statement, are true, provided that x is 5. Take a look. If I take a look up here and plug in x is 5, I get 8 parentheses 5 plus 3 equals 64. But we don't actually know if that's true. We don't know if this equal sign is right. It should be, because that's the point of an equal sign, but that's why x is 5. If I actually do this, I would get 8 times 5 plus 3 is 8, and 8 and 8 is 64. And so you can see the left-hand side and the right-hand side do in fact have the same value. And so this statement, 8x plus 3 is equal to 64 when x is 5. This statement down here, 8x equals 40, is true, provided that x equals 5. 8 times 5 is in fact 40. So you can look at these functions and see that at every point in time, the equality is constant, right? The left-hand side is 64, so is the right-hand side. The left-hand side is 40, the right-hand side is 40. X is the same as 5. This is the point of an equation, is that no matter what stage you're at in the equation, whether you're in the initial stage, after you've made one change, after you've made multiple changes, the equality of those statements shouldn't change. And the result is often the one time that you get that statement to be true. So in this case, when x is 5, the top statement works as a number, not a variable anymore. When x equals 5, the middle statement works as a number, not just a variable. And the last statement, of course, is our result. And so this is the process by which we know that this equation is done correctly, because it meets all of our expectations. Each side follows order of operations. When we cross, we have to undo those operations using reverse order of operations, with the goal being that the left-hand side and the right-hand side should always have the same value. Now, at each stage, the values changed, right? We have 64, 40, and 5. The values change, but what didn't change is their equality. The left-hand side and the right-hand side have the same value. So in the top one, 64 does equal 64 because x is 5. 40 does equal 40 because that's how x equals 5 works. And the bottom one is just the declaration of that statement. This is how you know you've done a problem correctly. Now, I would never advise doing all of these steps, simply because, well, it's a lot of work for the same results. But do note how that fits. And I will do this in the next problem as well, to kind of showcase how we know this process should work, so we can guarantee that the values do make sense. Let's take a look at the next problem. Okay, for our next problem, I'm going to keep some of our notes visible so we can see those. For our next problem, let's take a look at the following. We have 3x minus 2 equals 4 parentheses x plus 1. Okay. At its most basic level, the important thing to note about problems like these is that, again, each side can be treated separately using order of operations. So I can do every step possible to the left-hand side separately from every step possible from the right-hand side. And it is possible, when doing a problem like this, to simplify each side first, and is usually the step that I will go with. Second, the only time I have to worry about anything fancy is if I wish to cross the equal sign, if I wish to move something around. And I can do that by undoing the operation in reverse order operations order. So let's take a look at this problem. In this problem, I can see that my left-hand side cannot be simplified. 3x minus 2, we have two terms, a 3x and a minus 2. Neither of those combine. One has a variable with a coefficient, one is a constant. They are not combinable. But on the other side, I can see I have a clear example of distributive property. And so I will use distributive property to simplify this thing. Step 1, 3x minus 2. I did not do anything to it, so I'm going to leave it constant, equals 4x plus 4. Now I can see that my left-hand side has nothing to simplify, and that my right-hand side has nothing to simplify. Now, if I wish to cross this boundary that exists between these two functions, I have to use an undo operation, and it's best to go in reverse order of operations order. So, for example, I can move the negative 2. That is an option. I could move the 3x. That is an option. I could move the 4x. That is an option. I could move the 4. My goal with these kinds of problems is always I want all of the same variable on the same side, and secondary goal, all constants on the opposite side. This is your most basic goal. Let's take a look. In this case, that tells me that some of these are good, but some are not helpful. Like, moving the 3x is good, but if I move the 3x, I don't want to move the 4x. Moving the negative 2 is good, but if I use the negative 2 and the 3x, I haven't met my second criteria, that I want the constants on the opposite side. And so in this problem, I can choose two of these to be really good. And which two matters? I could choose moving the 3x to become the 4, as long as I also choose to move the 4 over. So I can move the 3x to be with the other x's, or I can move the 4 to be with the other constants. Or, alternatively, I could move the 2. But if I'm going to move the 2, I'd want to move the x's to get all the x's together. Those are my best options. Any other combination will not get closer to solving these goals. Remember, my goal is all the same variables on the same side, so all the x's on the left-hand side, or all the x's on the right-hand side. And then all the constants on the opposite side. So if all my x's are on the left, I want all my constants on the right. If all my x's are on the right, I want all my constants on the left. And note that no matter which order you do it in, you will get the same result. So let's look at these two. Let's try the first path versus the second path. The first path, I move the x's all to the right-hand side. So to do that, I would take 3x minus 2 equals 4x plus 4. I would subtract the 3x from both sides. And as a secondary step, I could also move the 4 over. I like doing them both at the same time because I'm crazy. And that makes it work for me. On the left-hand side, we have negative 2 and negative 4. On the right-hand side, we have 4x and negative 3x. I could then use the distributive property from last time in order to combine the right-hand side together, or you probably already did and got x. On the left-hand side, those are just numbers. I can just do the operation of subtraction. Negative 2 minus 4 would be negative 6. I've met my criteria. All the variables are on one side, and all the constants are on the opposite side. So this is an acceptable answer. Alternatively, I could have gone with a different path. 3x minus 2 equals 4x plus 4. I could have instead moved the 4x over and moved the 2 over. It'll give me a slightly different look, but that's okay. When I do that, I would have 3x minus 4x, which would probably go ahead and combine to get negative x. Versus on the right-hand side, I'd have 4 plus 2, which is, of course, 6. Now, you notice you have slightly different answers here. That's because this one is not actually meeting the second criteria. There is a constant here that we are missing. Remember, a negative sign is actually a negative 1, which means that if I wish to get this to be right, I want the variable to be by itself and all the constants on the opposite side. I have negative 1 times x. If I wish to move it, I have to use the opposite property. So instead of multiplying by negative 1, I get rid of it by dividing by negative 1. The negatives would cancel, leaving me with 6 divided by negative 1, which of course is just negative 6. And so we do end up with the exact same answer. So which process we choose to use isn't important. And notice that in this specific method, we don't actually care if x is on the right or x is on the left. We just care that x is by itself. We don't care if the negative 6 is on the right. We don't care if negative 6 is on the left, as long as the negative 6 is by itself. And again, we know this is right because it matches the first fundamental property of algebra. We should end up with the exact same answers if we do it correctly, even if we choose to do it in a weird order. Now, let's go back and revisit that concept we talked about before. How do we know x does in fact equal negative 6? Like, how do we know that's true? Well, if this statement is correct, that means the top statement is also correct, meaning 3x minus 2 does in fact equal 4x plus 1. And it works specifically when x is negative 6. Remember, the concept of equality is that the left and right hand sides are the same. And we can see that quite easily by simplifying this. 3 times negative 6 would be negative 18 minus 2. Negative 18 minus 2 would be, of course, negative 20. And on the right hand side, negative 6 plus 1 would be negative 5. And 4 times negative 5 is negative 20. And so the equality of the statement never changes. X equals 6 because negative 20 equals negative 20. If I came up with any other number here, like if somehow I did the math wrong and got x equals 1, then the equality of this statement would change. Because if x equals 1, then I don't end up with equality. I end up with 3 times 1 minus 2 equals 4, 1 plus 1. And that's not true. 3 times 1 is 3, minus 2 is 1. 1 plus 1 is 2. 4 times 2 is 8. This is not equal. Since this is not equal, we know that x cannot equal 1. It's that simple. The equality of this statement verifies the equality of the original statement, and vice versa. The equality of the original statement shows the equality of this statement. And that's how we know that this statement is true. Is because the equality we see here is the same equality as when we plug it back in. An equal sign, at its fundamental, means to have the same value. But it's also a check on your work. It's a way to verify that everything has gone correctly. Because if it has gone correctly, then the solution you got should work everywhere in the problem. Meaning every x in that problem should work. Let's take one more example. Like I said, this one should be pretty straightforward for you guys. Let's try something a little more out there. Let's see. For z minus 2z times 1 plus 4 equals 36 plus 2z plus 1. There we go. So, let's talk about this. In order to solve this problem algebraically, to get z by itself, remember the basic rules. Rule number 1. For each side, you have to follow order of operations. So the left-hand side of this function, I have to follow order of operations, meaning I have to do anything in parentheses first, right? First is parentheses. Second comes any exponents we have to deal with. The third comes any multiplication or division. Fourth comes any addition or subtraction. At any point in time, we may apply any of the properties we have. And same on the left-hand side. Okay? The left-hand side, I can simplify by using any of those steps. I can use parentheses, exponents, multiplication, division, addition, subtraction at any point in time, along with any of the properties, to simplify this side by itself. Only when I wish to cross this boundary do I have to actually worry about how to flip signs, do anything crazy. And so you'll see that for many of the math that I do, I don't flip until I've done everything I can otherwise. That does not mean this is the only way. It's just my way. Let's do it quickly, and let's see how we do. So, left-hand side. So this is my boundary line, because I want to make sure that the left-hand side, I'm only doing things on the left-hand side. Whereas on the right-hand side, I only do things on the right-hand side. I don't bother crossing that boundary until I'm sure the left-hand side and the right-hand side are right. So let's do this. Left-hand side. Everywhere that I can, I need to be able to use a property, or I need to be able to use order of operations. And so I see a parentheses. Parentheses comes first. And so I can take that 1 plus 4, and I can do that math first. Which means I would end up with 4z minus 2z with a 5 inside now. And on this side, you notice that I can't do that. There's nothing to simplify in the parentheses. And so instead, I'm going to go to a property. I'm going to use a distributive property. So plus 2z plus 2. And so with this problem, I did the distributive property over here. And on this side, I did the parentheses by simplifying. So, now let's look what we can do. On the left-hand side again. Well, I got a 4z, and I got a 2z, and I got a parentheses with a 5 in it. Okay, parentheses should have come first, but notice there's nothing to do in the parentheses. It's just a 5. And so parentheses are done. Now I look for any exponents. I don't see any exponents. Now I look to see if there's any multiplication. Well, 4 times z is 4z. But here, I can use the associative property to say that 2z times 5, I can do the 2 times the 5 first. 2 times 5 is 10. on the right-hand side. So again, notice that I just took this multiplication problem, which is 2 times z times 5. I can choose to do it in any order. I choose to do the 2 times the 5 times the z, switching the order around. And 2 times 5 is, of course, 10. And z is, of course, z. On the right-hand side, I see there's no parentheses left. There's no exponents. There's no multiplication or division to simplify anything, because 2 times z is just 2z. And so I can go to addition and subtraction as the last step. I see I have some addition that I can do, and I can do it in any order. So in this case, I can take the 36 and the 2 and put those together to get 38 plus 2z. But remember, the only reason I can do that is because I can take this problem and write it in any order because the associative property. In other words, I can take this 2 and move it next to the 36 and therefore add them together. 36 plus 2 is 38. Now that I'm here, I have 4z. Oh wait, but I can combine one more thing, right? I have 4z minus 10z. 4z minus 10z. I can use the shaded property and simplify. I would get negative 6 z. I do that all the time. Negative 6z equals 38 plus 2z. Now, I've simplified everything I can on the left-hand side, using every property and following order of operations. Same on the right-hand side. I've checked off to make sure that I can, in fact, do every single part of order of operations and every property. And this equality has not changed, because all I've done is simplify the left-hand side and simplify the right-hand side, meaning that this statement is the same as the one we started with. They are the exact same statement. Just one is simplified, meaning the equality that is between them doesn't change. At this point, now I can start to solve using my properties. My property stated, I want to put all the same variables on the same side, all the constants on the opposite side. Only practice can really help with this. Like, I have 3 possibilities. I can move the 6z to the right-hand side. I can move the 38 to the left-hand side. I can move the 2z to the left-hand side. But only one of those gets us closer to our goal easiest. My goal is to get all the variables on the same side. If I move the 6z over, it gets all the variables on the same side. But when I do that, it doesn't get all the constants on the opposite side. I have to take another step to do that. If I move the 38 over, it doesn't match either one of those categories. But if I move the 2z over, by subtracting 2z from everything, it would allow me to make the right-hand side just constants and put all the variables on the same side. It's negative 6z minus 2z, which is, of course, negative 8z. Okay, at this point, I can now take my last step, which would be to divide by negative 8 on both sides. Again, I divide negative 8 on both sides because it allows me to get to an answer that will match from top to bottom, in essence being negative 19 over 4. Simplifying fractions. Now, this negative 19 over 4 means that everywhere in this problem that I had a z, here, 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 and over here, everywhere in this problem that I had a z, if I went back and replaced it with negative 19 over 4, there's one thing that wouldn't change: the equality. Sure, the left-hand side and the right-hand side might be different on this line than on this line, but what matters is the left-hand side would match. This left-hand side might be negative 32, and this right-hand side might be negative 32, but this line might be negative 12 and negative 12. What matters is between them is an equal sign, and that equal sign is valid. It's how you know you've taken a problem and done it correctly, is that the pieces should match when done appropriately. That's our time for today. Our last major piece of big review from algebra, at least pre-algebra. And then next week we're going to be looking at some more advanced steps from Algebra 1 as well as from Algebra 2 to get us prepped for college algebra. I hope you guys have a good rest of the day. I'll see you at your Zoom session this afternoon from noon to 1. And don't forget, all homework assignments will be due as of noon tomorrow. That'll be Friday. I hope you guys have a good weekend, and I'll see you guys on Monday. Bye.